Hello there.
Good evening and welcome everybody, this is Obi-Wan Pez for in Simplex Pachinko. We are going to be doing some math stuff tonight, yet again working on cracking the GRE math subject test. We did let this go for a week when we were doing some exponential idle stuff last week. And maybe we'll get back into some coding at some point. I mean, we definitely will, it's just a matter of when. I also want to work on some more exponential idle stuff to, like, expand my knowledge about certain things on it. Try to pin down some of the, like, when are good choices to purchase things, you know, that sort of thing. Alright, right, cool. We're gonna start on start the talks about natural, exponential, and logarithmic functions. We did talk a little bit about it, I think, before, but okay. Basic idea is that we want to find some function y whose derivative is equal to itself, where y is not equal to 0. We also call that the trivial case. Pretty much any time that a function is equal to 0, we just call it a trivial case and move on. And what we're looking to do right now, see if we can find a particular function that's going to be a particular non-zero. Hey Zach, how's it going? There it is. So we know that y prime is equal to the limit as h goes to 0 of f of x plus h minus f of x over f prime at x is equal to that thing over h. So therefore, we're going to use I mean, we could go about this a couple of different ways. If we're assuming that we don't know what function has a derivative of 1 over t or 1 over x, that is one thing. I think we specifically have not dealt with it thus far in here. Pretty sure that was an intentional choice on their part. We may have done it, actually, but... yeah. So each of the u was an integral that we found earlier. That was an integral. What about derivatives? I'm sure there was a list. Yep, there we go. Yep. It explicitly says right in here what the derivatives of logs are, so. I think this is attempting to find sort of a pseudo Eulerian method of coming up with this particular function and its derivative. Ew. I'm like, A, let's do B. For the exponentials of the form b to the x, we end up with something that looks like b to the x plus h, taking the limit as h approaches 0. That's fine. Minus b to the x all over h. And that's going to be equal to, here we could separate out the multiplier, so b to the x times b to the h minus b to the x all over h, which is equal to limit. It's not the same if it doesn't have the limit. And then we take the limit of h going to 0 of b to the x, and then left with b to the h minus 1 all over h. It is then possible, because b to the x has no h in it whatsoever, it could just move outside. So b to the x times the limit as h approaches 0 of b to the h minus 1 over h. Right. So in this case, we know that this is going to be a constant. Of some form or another. Right, all basic exponential functions derivatives are constant multiples of themselves. Which means we're really close to finding a particular function whose derivative is going to be a constant multiple of 1 times the original function. So we totally don't know what it is. But what we want, right, is that the limit as h approaches 0 of b to the h minus 1 over h to be equal to 1. So that is our goal. Okay, so, right. So when h is approximately equal to 0, we're going to get something that looks like b to the h minus 1 is approximately equal to h. Then we're going to get b to the h is approximately h plus 1, and b is then therefore going to be approximately, parentheses, h plus 1 raised to the 1 over h. And the more astute students will remember that this is something interesting. If we were to do this as b being approximately equal to 1 plus h is going to be 1 over n, and 1 over h is n. So anybody who's done like the compound interest problem where you start looking at further and further values of n, we end up with some particular, oops, where did my calculator go? It was right here. Oh dear. No, here it is. I suppose we could pop it up in Desmos as well, but so if we pull up 1 plus 1 over x, right, raised to the x, and then go to the table, and we say, give me a, no, that's fine. Specifically, we want values where since h is going to 0, n is going to go to infinity. So we'll start with 1, 2, 4, 12. There's a reason I'm using these numbers. 365. 1 times 10 to the 6th. We'll go from there. Right, so Euler was coming across this, as were the Bernoullis, in trying to figure out what kind of number was going to then be the appropriate base to then get its own derivative as exponential derivatives. So here, if we plug in 1 to each of these places, we get 1 plus 1 is going to be 2 raised to the 1. It's going to get you 2. Okay, and then right, an n value of 2 is going to get you 1 plus 1/2, so 3 halves, raised to the second power is going to be 9 over 4, or 2.25. 4 is likewise going to be 5/4 raised to the 4th power, which ends up getting you a 2.44140.625. That terminates. 12 is going to be a 2.6130352902236. I don't think that terminates as it is, but it will eventually terminate. 365. Yeah, these are all fractions, so they will terminate eventually. 2.7145674820245. And a million for n ends up getting us 2.782804693193. As we get something that is absurdly large, can't do that. Really close. Anyway, 2.718281828459045. And that one does keep going forever. This is an irrational number. In fact, it is transcendental, meaning that there is no patterned way to get those individual numbers through your standard operations. In this case, we have to have a limit of this fractional value being raised to a higher and higher power. There is, in theory, well, I mean, when you get to do like Taylor series and stuff like that, you can have an infinite series of terms that will eventually add up to closer and closer approximations, and then at infinity it adds up to the exact value of e. Gave that one away. Exponential of 1, or e to the first, or anything else we can look at like this. It's the same stuff. So 2.718281828459045 is, as far as I know. Obviously, again, there are an infinite number of numbers after that. I do not have the E shirt. I'm sorry. Slacking. I suspect that it was named because of the exponential function being the basis of this. What derivative is itself the same function? However, a lot of people are like, well, it's Euler's number, so it was named after Euler. Leonard Euler, E. Probably not. Given that it was also used, I believe, by him during his lifetime, it seems a little maybe self-serving to be like, yes, the Euler number, it's E. And as much as Euler was himself, you know, famous, he did not cling to fame and use it as a lever as much as the Bernoullis did. Euler was not from quite as prestigious a family in Switzerland at the time, so he kind of rose up through the ranks naturally by showing his amazing prowess at doing all of this stuff. Okay. Okay, so the derivative ddx of e to the x will always be just e to the x, no matter what value x is going to be. So again, same deal with all of this up here. We're going to see that, again, the b to the h minus 1 over h has a limiting value of 1 when b is this e value. Found it! This also does allow us to write cool things like the differential equation that we had. Y prime is equal to y is going to imply that y prime over y is equal to 1. And then we can also end up saying, oh, well, this is dy dx over y is equal to 1. So therefore we can multiply both sides by dx and end up with dy over y is equal to dx. And now we have a very beautiful differential equation where when we take the integral of both sides, antiderivative in this case works just fine. We end up with, it's kind of giving it away, but all right. Nope. Natural log of y is equal to x. And then when we use e as a base, this will put all of that stuff into the exponents. And then e to the natural log of y, they're inverse functions of each other, so we just get y is equal to e to the x.
You could send a free chocolate bar in secret to someone special, just to, give them a little lift. With the Cadbury Secret Santa postal service, you can send free chocolates secretly from a poster. They're popping up all over the country. From great big cities to quaint little towns. Look out for a poster near you, or search Cadbury Secret Santa to find out more.
Right, or we could use the fundamental theorem of calculus. Natural log of y is going to be equal to That's not what that is. It's fine. Okay, this says, let A denote the area of the region bounded by the curve. Y equals 1 over x. The x-axis and vertical lines. X equals 1 and x equals a. Where a is greater than 1. In terms of a is the area. So bounded. Okay, so this is going to be capital A area is equal to the integral going from 1 to a of 1 over x dx. If we need to draw it out in order to make sure that we understand, we have here a particular sample rectangle that we're trying to find the area of. Its width is going to be delta x, and its height is going to be the function. Alright, so
We know what you're thinking. The whole nation is thinking it. You want more, Alan Carr. Well, good news. Changing Ends is back on ITV.
Alright, so what is the area that is so bounded? We have it right here.
The Guardian is raving, calling it
Right, taking the integral from 1 until a, whatever a is, of 1 over x dx. We could let that be a constant, or we could let that be a completely different variable, and then we say, okay, since it's a different variable, that means it's going to... Right, we have a dummy variable, we could substitute that out, and it will change variables.
If something isn't sitting right, you don't need to move or speak. Just text 6116 and it goes straight to the transport police. They'll get your message instantly and quietly. One text can protect you and the people around you.
By the fundamental theorem of calculus.
Easy to remember. Text 6116 for discreet help.
Okay, then
For your next journey.
this said if the vertical lines are x equals a squared and x equals a cubed, then what is going to be the area A of that bounded area? Right? X squared, x cubed? Yeah. So this is going to have the same integral that we had over there, but it's going to have a squared as our lower bound and a cubed as our upper bound, since a is greater than 1, right? A squared is going to be less than a cubed, so it's going to start at a squared, go to a cubed. Of 1 over x dx. Okay. So if we are to then use the information above, right, or just solve the integral best we can. This is going to get us, again, natural log of x. We're going to evaluate it at a squared and a cubed, and then we know that from the fundamental theorem of calculus we need to subtract the two things in order for them to be properly integrated using a definite integral like this. So this is going to be equal to the natural log of a cubed minus the natural log of a squared. And wouldn't you know it, the natural log, the entire point of using natural log, is to say that the thing on the inside is an exponential, and what is happening to their exponents. So there's a few ways to go about this. One would be that we could subtract 3 natural log a and 2 natural log a due to the fact that their exponents will come down to the front. We could also choose to make this a quotient of a cubed over a squared on the inside, and that's perfectly acceptable as well. Right, either way, we get that this is going to be the natural log of a just by itself. Right. So, next thing is what happens when we need to find Find the derivative of x raised to the square root of x. So in this case, again, we want to be able to say, in what way might we be able to make this a nicer function to take the derivative of? The issue with it standing right now is that it is both a power rule and an exponential rule at the exact same time. So there's not really a nice way to try and like make it work. So realistically, it's neither. We have to see what to do with it. So the first method, there are kind of two ways that I know how to do this. One was one that I found in the book, and the other is what I learned when I was both learning and teaching this, which is that we could let this equal y, and then take the natural log of both sides. So the natural log of y is going to be equal to the natural log of x to the root x. And as we just discussed over there, we can now, because of the natural log, bring the exponent down and multiply it in front. So this is the square root of x multiplied by the natural log of x is equal to the natural log of y. Take the derivative in situ, so exactly as it is right now, we just say, hey look, we're going to take the derivative of all this stuff. You could take it in, you could take the derivative as it is using ddx, and that'd be perfectly fine. I prefer using the generic derivative operator d. And then what you do here is you say, okay, if we were taking the derivative of the natural log of y in terms of y, right? What is that going to do for us? Well, the derivative of a natural log is 1 over the interior multiplied by the derivative of the interior, which the derivative of y generically is dy. And then we do the same on the right-hand side. So here, this is a product rule. So we're going to take the derivative of the square root first. The square root of x, we take the derivative, it's 1/2 x to the negative 1/2 times whatever we had to begin with. So don't change anything on the second one. Plus the first one, the square root of x, times the derivative of the second one. Derivative of natural log of x is then going to be 1 over x, and then times the derivative of x itself. I also forgot that on the square root as well. So both of these terms are going to have now a dx attached. And then if we want to take dy dx to be the derivative of y, the original function that we had, that's going to be then equal to, we would have to multiply by y on both sides. So y times, bracket, 1, that's really natural log of x divided by 2 root x plus root x over x. Alright, but y was the original function, so x raised to the root x. Now it's all in terms of x. Natural log of x over 2 root x plus root x over x. And in theory, if you really wanted to, you could rationalize denominator, do all that cool stuff. In this particular case, sure, why not, right? This could be a multiply the first one by root x over x. No, root x over root x. And that's going to get you root x times natural log x all over 2x plus this is way too involved, really. It doesn't matter. Let's do 2 root x over 2x. That way we can take out a 2x entirely. From the denominator. X to the root x over... I mean... Nah, you know what? Let's back that up. Go the other way. So let's multiply by root x over root x here. That makes the root x on top, since it's squared, it's just going to become x. And then we already have an x on the bottom for that second one, so those get divided out. And then we're left with 1 over root x, which is nicer. So let's fix that. This is going to be a natural log of x over 2 root x plus 1 over root x. Then we can make this a 2 over 2 root x. Pull that out. I get 2 root x on the bottom. And then we get natural log of x plus 2. Realistically, right, like this one was perfectly fine as well before the things got crossed out. Right, so then the other option, which is the one that they teach in the book, is instead of x root x, right, this is y equals x to the root x. Instead of this, we could rewrite this as e raised to the natural log of x to the root x. So this is just doing the logarithmic stuff in the exponent without having to like take the log of both sides, do an implicit differentiation of y, which is not hard, but you know, this keeps the problems in one place. So this is going to be y equals e raised to the, again, root x comes down times natural log of x. If we take the derivative of both sides, e raised to all that is just going to remain itself when we take its derivative. But then we have to multiply by the derivative of that exponent. Which again makes it 1/2 x to the negative 1/2 times natural log x plus x to the 1/2 times natural log of x, take its derivative is 1 over x. Yeah, right. I just did it with the symbols instead of the numbers. Y prime is equal to e to the root x times natural log x multiplied by, in here, we're going to have a again, natural log x over 2 root x plus, alright, this is going to be a 1 over root x, which again, depending on how you want to do this stuff, it could be left as e to the root x times natural log x, or it could be recombined back into x to the root x. Let's see, what do they do? Yeah, they do that eventually, so. They also take the root x out and put that on the bottom. And leave it as natural log of x over 2 plus 1. Which is, again, same thing that we got over here. So, the one on the left ended up taking out the root x in the denominator, but also a 2, which would make the stuff on the inside twice as big. So instead of a half natural log of x, it's just natural log of x. Plus 1 now doubles to 2 when you take out that half. So, if anybody has any particular questions, let me know. We are... coming up to a section break. Should also be a reasonable break to have between, yeah, be a reasonable place to have an ad break. So, let me know what you got. Let me know if you're interested in working on anything in particular, and see what we can do. See if I'm stretching anything. I think this is actually a better height. Something like that. Anyway. Okay, so The example they use in the book is actually pretty terrible. They say if we have a limit such as when x goes to 1, we want x minus 1 over root x minus 1. Right? This is a terrible example, not because direct substitution yields 1 minus 1 over 1 minus 1, which is 0 over 0. That's actually expected. This is what we call indeterminate form. I don't even know how much I didn't speak. Cool. Okay. The problem with this particular limit is not the fact that when you do direct substitution, you get 0 over 0, which is an indeterminate form. That's to be expected. Pretty much all of your hardest limits are going to be of some sort of indeterminate form. The issue with indeterminate form is, again, most simply that you can't figure out what it's going to do. So it could be going off to infinity, or it could be going to a finite number, or it could be going to 0, which is also a finite number, but a specific finite number like 0. And depending on the behavior of your problem, think about rational polynomials, right? If we have a polynomial divided by a polynomial, there are 3 major behaviors. One is that if the degree of the numerator is higher, then its end behavior is to go off to infinity, whether positive, negative, or one of each. If you have degrees on your polynomial that are the same, then it is going to go to a finite value that is not 0. The most basic one is just 1. Again, it's going to be the coefficient, ratio of the coefficients of your leading term, ratio of your lead coefficients when the degrees are equal. And if the degree of the denominator is lower, if the degree of the denominator is higher, then that rational polynomial or rational set of polynomials is going to have end behavior at 0. So here for this one, our indeterminate form is 0 over 0. However, it's easy to see for this particular one that this is equivalent to the limit as x goes to 1 of root x minus 1 times root x plus 1 over root x minus 1, which becomes determinate. Right? This is going to be root 1 plus 1, which is just 2. Now, in theory, you could also do this using this L'Hopital's rule thing. You could solve it using this L'Hopital's rule thing and make sure that we also get 2 here. So we could just verify it, make sure that it does work the way we think it works. So, pretty decent one for this. Alright, L'Hopital's rule, I guess I didn't really state it beforehand, but it's okay. Right, we want L'Hopital's rule, which is the fact that we have a limit as x goes to some value, so call it c, of the ratio of two functions, f of x to g of x. This is going to be identical to the limit as x goes to c of f prime at x over g prime at x. So we do have a formula for derivatives. Right, so the limit as x approaches c of f prime at x is what do we get as the derivative of a particular function is going to go to what's the derivative of the function when the individual x value goes to a particular location c. So for this is going to be f prime at c effectively, which is also the limit as x approaches c of f of x minus f of c all over x minus c. All right, and similarly for g prime at c. So here we've got these two things. Limit as x approaches c of f at x minus f at c all over x minus c all over g at x minus g at c over x minus c. These two, x minus c, end up going away. And where f of c equals g at c equals 0, we end up with identical values. Those drop out, and we get the exact same thing left and right, which I'll write now. I'll see you in 3 minutes. So, ad break. Everybody get up and stretch and stuff. See you in a few.
You know the drill. End of series, credits roll, the next ITVX show begins. But how can you move on when everyone's still talking about it? Fake has captivated critics.
Okay,
It's a
well.
romance scam thriller where a writer discovers her date is hiding dark secrets. Digital Spy calls it an aggravatingly addictive watch, while The Guardian says Asher Keddy deserves every kind of award. Some shows end at the credits. Others get everyone talking. Stream Fake, now on ITVX.
Right. So, Taichi did more of the form today. A couple extra steps anyway. So, anybody else who's interested, warm up with me, right? Let's also swap. Ever so slightly more that way. Right. So generation of power is always a little bit of fun to try and figure out for yourself. I do recommend doing Tai Chi at some point because it's pretty freaking awesome. And if you've ever done any other martial art before, it really helps you focus yourself and try and figure out where all your power is coming from, where it's all going to, and how to optimize some of that movement. So, now my instructor went to Malaysia for quite a while, so yeah, he learned from like some of the absolute masters. I don't necessarily recommend that, but you know, if you got the opportunity, go for it. Again, the purpose of all of this stuff is to kind of loosen up your joints and get all of the muscles a little bit warmed up, all the while, again, trying to utilize hip motion back and forth in a sort of minimalistic kind of way in order to build energy and try to get your hands to move fast by themselves. So rather than having to force your hands up or moving them yourself, you're just kind of letting it go, letting it do its own thing. And again, based on the ability for your body to generate power, right? You want to just let those arms relax almost completely. And try not to let them like smack yourself or yank really hard on the way down. Got a lot of clicky noises in my shoulders. Alright, so the form. Start with heels almost together and toes facing more or less out, and then we just from this kind of neutral position bend into the right inguinal crease, kind of lower that hip just a little bit, step out, and then get into a shoulder width stance. Arms come up, push back and down, and then from here you pivot on the right foot, grab an energy ball coming this way, step, and do a left ward off, and right arm just comes down underneath like this. Then we want to work into the crease again, and then step back one more time with now a right ward off, and left is gonna left hand's gonna point at the right one, and then we're going to turn on the heel, which now puts us in a much more forward position rather than turning on the ball of our foot, which kind of, as does in my art Tang Soo Do, kind of leaves us with like being able to drive through the ground, but it leaves us with a longer stance. And so if you use the heel to pivot, you end up much closer and much more forward. So we're about here. We do a roll back, press, push. Then as we lean back, we're going to come across this way and turn on our ball of our right foot. And from here, we come down this way, turn on the ball of the foot this time, and do a single whip. So it's going to use the back of the wrist in order to do like a striking move. And then we come out in front of us this way as we step into a wide open stance here. And then we're going to again turn on the heel of our right foot and twist the hand around and shift our weight forward all at the same time. Then we're going to bring these down and move up. Oops, no, don't shift your weight. And bring the hands up like this. Prepared to move, defend, whatever it is. And then here, we're going to, this is the new stuff that I learned. We twist the hands about 45 degrees in, drop them down, bring the heel back, and then we're going to do a step in. And this is that same shoulder strike, which is going to allow us to strike with the shoulder into someone as well as letting the arm fly. As we know, can be painful. This is going to be pointed toward the front of the room. That's going to be pointed toward the side of the room, 90 degrees. And it's a pretty wide stance, all things considered. So we end up, left hand is going across the body, essentially prepared to either block, strike out, or do anything else you want to. Right, so I think that's everything. So we'll start from the beginning again.
But I will not get down, for you can't force me now.
Something to that effect. Cool. Okay. So we use the definition of derivative to prove L'Hopital's rule as long as the particular point f of c and g of c is a zero of those particular functions. So the issue is that, again, when you try and plug in x going to whatever value that is, we're going to get a zero value for the function. We're also going to get a zero value for f of c. So the function, when we plug in the zero value directly, and also the limit is going to be 0. So if it's not, the proof ends up being a bit more onerous. But effectively what we can do is just take the function and shift it up or shift it down based on that value to anywhere we want in the plane. It doesn't have to be 0 now.
Nothing could have prepared me for the high stakes heartbreak that surrounds me. You want me, you won't let me go. So
There is actually a whole nother proof that uses epsilon delta, and a whole nother proof that uses a dummy variable t inverse in order to make all this work. T inverse is for when you have an infinite value. And so we can invert the particular number that we want from being equal to 0 to being equal to infinity at those particular values, having limits at infinity. Okay, so the upshot of all this is that we know that the limit as x approaches some c value of f of x over g of x is going to be equal to the limit as x approaches c of f prime at x over g prime at x. Right. So if we do this, and we use our stuff from earlier, we had the limit as x approached 1 of x minus 1 over root x minus 1, then this should be equal to the limit as x approaches 1 of, take the derivative of the top, right, d dx of x minus 1 over d dx of root x minus 1. From above, we knew that this should be 2. So what does that mean in terms of what we've got here? Well, ddx of x minus 1 is just going to be 1. So take the limit as x goes to 1 of 1 over, and in the denominator we have x to the 1/2 now becomes, just as we did all these other times, 1/2 x to the negative 1/2 right? And if we let x be equal to 1, then we find that the denominator is just going to become 1/2 times 1. So this is the, nope, don't need the limit anymore because we've already taken it. It's going to be 1 over 1/2, which is equal to 2. And so verified. Hey, Academy of Useless Ideas, how we doing tonight? Good evening and welcome everybody. My name's Obi-Wan Pez and this is N-Simplex Pachinko. In case you haven't seen us before, we're doing some cracking the GRE, which is the Graduate Record Exam math subject test. If you are planning on becoming a graduate student, hey Pen.
I have a pen. I have an apple. Apple pen.
If you have intention of becoming a graduate student, most of the time in the US they'll have you take the graduate record exam and make sure that your abilities are up to snuff. So the GRE is going to be one of those tests that probably you're taking if you're going into grad school. Maybe not. We'll see. Let's see. We were just talking about L'Hopital's rule. We were doing a simplification of L'Hopital's rule where we said that the rule is that if you take the limit as x goes to some value c of f of x over g of x as a quotient, then the individual derivatives will have the same quotient when you take their limit at that same c value. And the simplification of this went with, well, let's try to find the derivatives of these functions at c. And so the derivative f prime limited where x is going to c can be rewritten as the limit as x goes to c of f of x minus f of c over x minus c. And likewise for g, and those x minus c's divide out, and then if f of c equals g of c equals 0, then these two things divide out, or these two things become 0, and then we're just left with a tautology. Now, it is a simplification. It doesn't always work. And so there are a couple of other proofs that get you to the full L'Hopital's rule, both in times when those functions are both 0 at c, when they are a finite number at c, which is not 0, and also an infinite number, because we could invert that particular function and say, well, let's find it at 1 over a particular value. So we could use any of those. Right, then we looked at the example that we had from the start, which was the limit as x goes to 1 of x minus 1 over root x minus 1, which we found is 2. We also found this via the standard method, which is factor it, and then divide out the offending term. So our root x minus 1 could be divided out from top and bottom, leaving behind a root x plus 1. When you plug in 1, you get 2. Right, and there are all sorts of indeterminate forms that you can work with to make this turn out to be what you want. What we can do is also look at the other examples which are in the book. So this is going to be the limit as x approaches 0 of the sine of 4x over x, nope, over x, which is going to be the same as the limit as x goes to 0 of, take the derivative of each bit. So the sine of 4x is going to be cosine of 4x times 4 divided by, take the derivative of x, it's 1. Right, so as x goes to 0, cosine of 0 goes to 1, and so we get 1 times 4 over 1, which is just 4. Okay, b, taking the limit as x goes to 1 of the square root of x minus 1 over the cube root of x minus 1. That's not nice. It's okay. Right, if we take the derivative of both the top and the bottom, the top gets us 1/2 x to the negative 1/2. Oops, limited. Limit x goes to 1 of 1/2 x to the negative 1/2 over 1/3 x to the negative 2/3. If we plug in 1s into both of those terms, then the x terms are just 1. And so we end up with 1/2 over 1/3, which is 3/2. Now, in theory, yes, you'd actually probably want to check whether it is, in fact, indeterminate first. So plug a 1 into both top and bottom there. You get square root of 1 is 1, cube root of 1 is 1, and then they're both 1 minus 1, which equals 0. So you get a 0 over 0. It's indeterminate. Next one. Limit as x goes to 0 of x squared over 1 minus cosine of x. Again, same deal, 0 divided by 1 minus cosine of 0. Cosine of 0 is 1, so 1 minus 1 is 0. 0 over 0 is indeterminate. Then, we say by L'Hopital's rule, the limit as x goes to 0 of, take the derivative of the top, it's going to be 2x. Take the derivative of the bottom, it's going to be a positive sine of x. We take that, and when you plug a 0 in top and bottom, it is again 0 over 0, which is indeterminate. So we do it again. So take the derivative of the top, and it becomes 2. Take the derivative of the bottom, it becomes cosine of x. And we take 0 and plug them into all x's, we get 2 over 1, which is just 2. What about the limit when x goes to infinity of 1 over x times pi over 2 minus arctan of x? Okay, if we look at infinity, then we have x is infinity, and arctan of infinity becomes pi over 2. So pi over 2 minus pi over 2 is 0. 0 times infinity in the denominator. So this is another indeterminate form. So if we take the derivative of both top and bottom, well, there is a little bit of a problem there. The top is going to become 0. So instead what we do is we say, okay, hang on. Take the limit as x goes to infinity of 1 over x on the top and pi over 2 minus arctan of x on the bottom. Okay, so now when we take the derivative of both the top and the bottom separately, we get the limit as x goes to infinity of, this is going to be negative 1 over x squared. And the denominator is going to become negative 1 over 1 minus 1 plus x squared. Ooh, it's been a while. 1 plus x squared. Yep. So this is now going to become the limit as x goes to infinity of, here we could multiply both top and bottom by the respective terms in order to get rid of those fractions. So up top we get 1 plus x squared, and on the bottom we get x squared, and we lose the negative from both. Okay, so for this, we can go back to pre-calc on this one and say, all right, look, I've got a rational function here, and the numerator and denominator are polynomials which have equal degrees. Their leading coefficients are both 1, so this should be 1. If you don't believe me, you can always take more derivatives. So here you take the derivative once, you get 2x over 2x. Take the derivative again, and you get 2 over 2, which is 1. Basically, you try to stop as soon as you can. But infinity over infinity is also indeterminate. Right, so infinity over infinity is also indeterminate. Although we have ways of dealing with this one, because again, we've done this before. The other option with this, again, there are a bunch of different ways. So you could have said that this is 1 over x squared plus 1, taking the limit as x goes to infinity. We could have gone with the if it were a larger polynomial on the bottom, it's more of an option, but you could have done, 1 over x squared plus x squared over x squared over x squared over x squared, which again equals 1. You could also do then L'Hopital's rule, which says the limit as x approaches infinity is going to be 2x over 2x. We could stop there and cross them out, and they're 1. Or you could take the derivative again, as I said, as x goes to infinity. And we get 2 over 2, which again, still 1. If you ever end up doing this in 2 different ways and you get 2 different answers, you need to look over it again. Most likely the biggest error that students make that I've seen is that they take L'Hopital's rule even when something is determinate. So as soon as it turns from indeterminate to determinate, stop. Don't do anymore. Right, and what about the limit as x goes to 1 from the positive direction of x to the 1 over x squared minus 1? Right, so this is another one of those that ends up not working in the default manner. If we try and just plug a number in, we're going to get 1 on the positive side, raised to the 1 over 0, which is infinity, and seems like that should go to infinity. But it is still indeterminate. We don't know entirely. So what we need to do is go into this and create a numerator and denominator and break this apart into those two parts. Take the derivative of each part as L'Hopital's rule says, and we'll figure this out. But we don't know what this is yet. So one of the things to do is fall back to what we did above, which is we say that the interior of this is going to be e to the natural log of x raised to the 1 over x squared minus 1. Since it's a natural log, that means that this is going to be the limit as x goes to 1 from the positive side of e raised to the 1 over x squared minus 1 times natural log of x. Right, so then this is going to be the limit as x goes to 1 from the positive side of natural log of x over x squared minus 1. Nope, e to the... Totally. 100%. No notes. Okay, so there's a number of different ways to do this. Again, this is just one of them. Using the GRE book's method of finding limits for tower functions like this, we're going to take this as e to the natural log of that same thing. Makes it break up rather nicely. And then here, again, we could just say, well, this limit doesn't affect e at all. So now this is the limit as x goes to 1 from the positive direction of natural log x over x squared minus 1. Oh, look at that, it's a fraction. Which means that we just take e raised to the, now we're taking this limit and doing L'Hopital's rule on this limit. Is it in fact an indeterminate form? Easy enough. Plug in 1. Same deal. Natural log of 1 is 0, and then 1 squared minus 1 is 0. So 0 over 0, it's indeterminate. Cool. Limit x goes to 1 from the positive direction of. What's the derivative of natural log of x? It's 1 over x. What's the derivative of x squared minus 1? It's 2x. Right? Multiply both top and bottom by x. Okay, this means we get e to the limit as x goes to 1 from the positive direction of 1 over 2x squared. As x goes to 1, there is no difference from the positive or negative direction for this particular function, a quadratic. Right? 2x squared, it's going to the same value. So this is going to end up being 1 squared is 1 times 2 is 2, so that's 1/2, which makes this e to the 1/2. Square root of e. Let's see. The one that I used to do... also set this equal to L, and then said we want the natural log of x to the 1 over x squared minus 1 limit x goes to 1 from the positive direction equals the natural log of L. So here again, this is going to be the natural log of x multiplied by 1 over x squared minus 1, and that's equal to the natural log of L. Take the derivative, again, limit x goes to 1 from the positive direction of 1 over x over 2x. So limit as x goes to 1 from the positive side. Multiply both top and bottom by x. Again, it's just 1 over 2x squared, which is equal to the natural log of L. This is equal to 1/2. And then we're going to raise e to both sides, and we get that L is equal to, the limit is equal to e to the 1/2. So, a whole bunch of different ways you can make it work. It's all basically the same stuff. Right. Anybody have any questions?
Your usual tunes can wait. It's Christmas after all. Pepsi Max, thirsty for more.
Okay. One last one. Which also will eventually come into play, but just not today. This is... find the limit of the sequence. A sub n is equal to natural log of n, parentheses squared, all over root n. Right, comma if it exists. It's always fun to put that on there because the students get suspicious immediately. So for this particular setup, there is a rule. A sub n converges if and only if the continuous function where these are all equal to each other, f of x and a sub n are all equal for every possible value, converge, right? So if f converges, a sub n must converge, and also if a sub n converges, then f of x must also converge. So practical upshot here is that our goal is to find limit as x goes to positive infinity of f of x, which equals the limit as x goes to infinity of natural log x parentheses squared over root x. Equals L, right? So, is it indeterminate as it stands right now? Natural log of infinity is infinity. Square it, it's also infinity. Divided by the square root of infinity is also infinity. So yes, infinity over infinity is indeterminate, so we can use L'Hopital's rule to try to make this easier. Next question. Is it easier to just say, hey, let's find what happens when we take the derivative of the top and the bottom? Let's find out. Natural log x parentheses squared over root x should be equal to, then, the limit as x goes to infinity of, take the derivative of the top. You get 2 natural log x times 1 over x. Denominator then becomes 1/2 x to the negative 1/2. Okay, which is going to be equal to, if we just simplify, don't change anything, multiply both top and bottom by 2, we get 4 on the top and 1 on the bottom. Multiply top and bottom by x, and we get natural log x on top and x to the 1/2 on the bottom. So effectively, the only thing that changed here is the coefficient sitting out front based on the exponent that used to be on the natural log. Interesting how that one works. So then we take the derivative again, and this is going to be 4 times 1 over x all over, again, 1/2 x to the negative 1/2. Again, multiply both top and bottom by 2x. And that is going to get us an x to the 1/2 on the bottom. And on top, we're going to have an 8. This is no longer indeterminate, right? Infinity plugged into this is going to get us an infinity in the denominator and a constant in the numerator, which means that this is going to go to 0. Now, I did already know this, to be fair, because the hierarchy of functions is going to tell us how all of this stuff works. So what is going to be faster than what? Natural logs are pretty much at the bottom. After natural logs comes rational exponents, powers, and then above powers are higher powers, and then above those powers are
still talking about it.
exponential.
Has captivated critics.
I think that's the next one.
Romance scam thriller where a writer discovers her date is hiding dark secrets. Digital
Exponential and then tower above that.
Well, The Guardian says Asher Keddy deserves every kind of award. Some shows end at the credits. Others get everyone.
So tower functions are usually at the top.
Stream Fate.
What most people are not going to. What most people are going to run across in their regular calculus days. There is the possibility of having like factorial functions or something ridiculous like that, which are also very fast. I think that they're faster than tower functions, but I can't remember exactly.
Why is it frozen? Why? It's for 40 degrees below. Or did you think we were standing here for fun?
Cool.
Red Bull gives you
Right.
wings, but only if you drink it.
Cool. I think that will probably do it for tonight. So, I may come back tomorrow and work a little bit more on 9 Souls, just to see if we can get past the twins and not have to wait 2 weeks. We'll see how things go. Either way, this Friday we're not going to be here. We're going to be heading to Marrakesh and go hang out in Morocco for like a week. We'll be back just before Christmas, and yeah, we'll see you all around Christmas, whenever that is. That was a stupid thing to say. No, you know what I meant. Let's go say hi to friend of ours. Ooh, Maddie Braun is playing Control. That's a good one. He's only like an hour in, so nice. We're going to go over and see Maddie Braun. Hope you all have a good rest of your week. Again, maybe see you tomorrow. And if not, I will see you next week. So have fun, everybody. Merry Christmas if I don't see you. And happy holidays if I don't see you longer. Have a good night. My name's Obi-Wan Pez. This is N Simplex Pachinko. Night.